What if a single, 3 billion parameter model could find anything in any image, detect every car in a crowded intersection, read the text off a diagram, point at a button in a user interface? That model exists. It's called LocateAnything, from NVIDIA's Eagle family. And in this video, we're not just going to admire it from a distance. We're going to install it on a consumer RTX 4090, run it, break it, fix it, and build a working demo around it. Let's go. Chapter 1. The model itself. Before we touch a terminal, let's understand what makes LocateAnything different from every other vision language model that claims it can detect objects. So what is LocateAnything? It's a generalist grounding model, one network that handles many different localization tasks. Under the hood, three pieces work together. A MoonViT vision encoder looks at your image at its native resolution, no squashing everything down to a tiny square. A Qwen2.5 language decoder reasons about what you asked for, and a small MLP projector bridges the two worlds. It was trained on a staggering 138 million language queries and 785 million bounding boxes. And here's the kicker, it's only 3 billion parameters, about 7 gigabytes of VRAM in float 16, that fits on a gaming GPU. Now for the big idea, the reason this model is fast. Classic vision language models treat a bounding box like a sentence. They generate X1, then I1, then X2, then I2, one token at a time, each waiting for the last. LocateAnything says, that's silly. A box is one geometric object. So Parallel Box Decoding predicts the entire box, all 4 coordinates, as a single atomic unit in one forward pass. That preserves the geometric coherence between the corners, and it unlocks serious speed, 12.7 boxes per second on an H100. That's roughly 10 times faster than Qwen3 VL at the same task. Everything the model says comes out in a tiny, parsable grammar. A detection is a ref tag with the label, followed by a box tag holding 4 integers. A point is just 2 integers, and if nothing matches, you get box none, an honest, empty answer. The clever detail: coordinates are integers from 0 to 1000, normalized to the image. That means the output is resolution independent. Divide by 1000, multiply by your image size, and the boxes land exactly where they should, no matter how big the original picture was. 10 lines of Python, and you've got pixel-perfect rectangles. Chapter 2. Generation Modes. LocateAnything gives you a dial with 3 settings: fast, slow, and hybrid. Knowing when to use each one is the difference between a snappy demo and a frustrating one. Fast mode is pure parallel box decoding, whole boxes in single steps, maximum throughput. It's built for robotics and live agents where every millisecond counts. The trade-off: in extremely dense or ambiguous scenes, the parallel guesses can occasionally stumble. Slow mode is the opposite philosophy, classic next token prediction, one coordinate at a time, just like a regular language model. It's the most stable option, perfect for offline labeling jobs and benchmark evaluations where you'd rather wait than retry. But you pay the full sequential latency price on every single box. And then there's hybrid, the default, and honestly the clever one. Hybrid runs in fast mode, but it watches its own output like a hawk. The moment it sees malformed syntax or spatially ambiguous coordinates, say 2 boxes blurring together in a dense crowd, it discards the compromise block, rewinds to the last verified prefix, redecodes just that block in careful token-by-token mode, and then switches right back to fast. You get nearly all the speed of parallel decoding with the reliability of sequential decoding. Use hybrid unless you have a very specific reason not to. Chapter 3. The tasks. This is where a generalist model earns its name. Same weights, same prompt format, 5 very different jobs. Let's see real outputs from our own machine. Task 1. Object detection. You hand the model a list of categories: car, person, traffic light, bus, truck, and it returns a labeled box for every single instance it can find. This is our actual output on a busy Tokyo intersection, generated on the 4090. Dozens of people, vehicles, and signals, each one boxed and labeled in a single pass. And the category list scales. We verified 218 categories in one query on this very machine, and the model echoed back an answer for every single one. Task 2. Phrase grounding. Instead of fixed category names, you speak naturally. Ask for bus in multi-mode, and every bus in the scene gets a box. Here it found 3. But the single mode is where it shows off. Ask for the green bus closest to the camera, and the model has to understand color, understand depth, compare candidates, and hand back exactly 1 box. That's real language understanding driving real geometry, attributes, spatial relations, and superlatives all resolved inside 1 forward pass. Task 3. Scene text detection. 1 fixed prompt. Detect all the text in box format, and the model sweeps for writing. Here we pointed it at the paper's own architecture diagram, and it came back with 54 text regions. Look closely at the labels. Each box's label is the transcribed text itself. So this isn't just where is the text, it's where and what. Document layouts, street signs, user interfaces, same trick everywhere. Task 4. Pointing. Sometimes you don't want a box, you want a single coordinate you can click. We fed the model a screenshot of our own demo app and asked it to point to the orange locate button. And there it is, a dot, dead center on the button. This is exactly the capability that GUI automation bots and embodied agents are built on. See a screen, understand an instruction, produce a click target. The model scored 60.3 on Screen Spot Pro, beating GUI specialists 10 times its size. Numbers on our own hardware, not a marketing slide. Fast mode pulled 65 boxes out of this scene in a single parallel pass. A full hybrid detection over a 1920 pixel intersection lands in under 10 seconds on the 4090. Tight, single phrase grounding queries come back in 2 to 3 seconds end to end. And in our demo app, there's a bonus feature we added. Every detection can be automatically cropped out of the full resolution original and saved to disk, organized into folders by type. 1 click, and you've got a labeled image dataset. Chapter 4. The install. This model was born on H100 clusters. Our mission was to make it feel at home on a single consumer RTX 4090, on Pop OS, with a clean, reproducible environment. Here's the exact recipe. Step 1. The environment. We pin everything locally with asdf. Python 12.8 and of 088 written into a tool versions file that lives with the repo. Then OOV creates a dedicated virtual environment inside the project. No conda, no global site packages, fully disposable. And we hit our first gotcha immediately. A stray of binary in local bin was shadowing the asdf shim, silently giving us the wrong version. The fix is boring but bulletproof. Call the asdf shim by its full path. First lesson of reproducible setups. Never trust bare commands on a machine with history. Step 2. Install order matters. Torch goes in first from the CUDA 12.8 wheel index. That lands Torch 211 with full GPU support. Only then do we install the repo itself, which pulls transformers for 57 deep speed inference, and crucially, doesn't downgrade our Torch. Then the golden rule. Verify before celebrating. 1 line of Python must print CUDA available, true, NVIDIA GeForce RTX 4090. And 1 more house rule. Every model download is forced into a dedicated cache directory on the big drive, so 7 gigabytes of weights never lands on the system disk by accident. Step 3. The moment of truth. The checkpoint downloads 7.2 gigabytes and loads into just over 7 gigabytes of VRAM in bfloat 16. We pass 1 critical override, which we'll explain in the next chapter, and fire the first detection at the Tokyo intersection. 97 boxes in 9.7 seconds. NVIDIA SME confirms the GPU is doing the work. From empty directory to a working state-of-the-art grounding model. About 15 minutes, most of it download time. But getting here wasn't actually this smooth. And that's the next chapter. Chapter 5. Everything that went wrong. 10 distinct issues stood between us and that smooth demo. Here are the 3 best war stories, and what each one teaches. War Story 1. The Hopper-only default. Read the model's configuration code, and you find the attention backend silently defaults to MAGI. Mega Attention, a blazing fast kernel that only exists for data center, Hopper, and Blackwell GPUs. Our 4090 is the 8th generation. No MAGI for us, and the worker class doesn't even expose the setting. The fix, pass attention implementation SDPA when loading the model, falling back to PyTorch's built-in scaled .product attention. One keyword argument, but you have to know it's there. And now you do. War Story 2, the best one. A user uploads a big image, and the GPU asks for 40.6 gigabytes on a 24 gigabyte card. Where does a 3 billion parameter model get the nerve? Here's the chain. The vision encoder works at native resolution. Big image, up to 25,600 tokens. The SDPA fallback then builds a dense attention mask, which kicks PyTorch down to its math backend, and that materializes the full attention matrix in float 30. 16 heads times 25,600 squared times 4 bytes, 41 gigabytes. The error message matched our arithmetic to the decimal. The fix, cap the processor's token limit at 6,400, so huge images get downscaled before the encoder. A 6,000 pixel image now runs in 2.2 seconds. And because the output coordinates are normalized, the boxes still land perfectly on the original. War Story 3. The demo itself. The repo ships no local UI, so we built one with Gradio and walked straight into dependency whack-a-mole. The pinned Gradio version is from 2023 and crashes against modern Jinja 2. Upgrading Gradio dragged in a 2 new Hugging Face hub that broke transformers. Pinning hub back down fixed both. Then the model occasionally emits boxes with inverted corners, which the drawing library flat out refuses to render. One sorted call fixes that. Every single fix was one line. Finding each line, that's the actual work, and that's why we documented all 10 issues with their exact fixes in the notes folder. And here's where we landed. A complete local demo running on the 4090. 5 task types in a dropdown, all 3 generation modes a click away, a token budget slider for dense scenes, and one-click examples for every capability, including pointing at its own interface. The crop feature slices every detection out of the full resolution original and files it into folders by type with a ZIP download. The whole thing idles at about 7 gigabytes of VRAM. A frontier grounding model, a working tool, and a documented install, all on one desktop GPU. That's LocateAnything, one small model, 5 localization tasks, 3 decoding modes, and a 4090 in a desktop tower doing work that used to need a data center. Everything you need is in the official NVIDIA repo, github.com/vlabs/eagle, and the model is open on Hugging Face, NVIDIA/LocateAnything-3B. Go point it at something. Thanks for watching.